Now let's talk about what happens if I take some of the assumptions away, and specifically what happens if I don't radiate in free space, or even when I don't have line of sight. So there are two particular examples that you can see in those slides. There is one example here where you have the direct line of sight communication, but you also have a reflected power that may reach the antenna. In this particular case, this is given by ground reflection. And there are many cases where those two particular beams or other paths are dominant. So if you're driving, for example, your car in an open space, that reflection from the ground and the line of sight path are going to be the main two dominant paths. Of course, you might have reflection from trees or the car itself, but the reality is that you will have two main dominant paths. Unfortunately, the reflection from the ground usually changes the phase close to 180 degrees, and that means that it actually adds distractively to the main line of sight path, which means that now you have two competing signals adding 180 degrees out of phase. So when that happens, we have what's called the Riccian fading, which essentially leads to a propagation loss of roughly 1 times distance to the cube, instead of 1 times distance to the square, which is the direct phase transmission equation. There are also many more complicated scenarios. If, for example, now you're driving in a big city, you may or may not have the line of sight path shown here, but then you won't have just one dominant reflection, but you will have multiple reflections. And those multiple reflections are not even constant in the sense that you're moving all the time. And so you basically have a very, very messy multipath propagation scenario. So normally we will try to represent this as 1 over d to the 4. Sometimes it could be 1 over d to the 5. Sometimes it could be 1 over d to the 6, depending actually of how well positioned you are compared to the transmitter. But my point is that normally what people will do is that they will assume, either based on some modeling or some type of a measurement, that the propagation loss is basically something in the order of 1 over d to the n, where that n is going to be greater than 2. 2 is the ideal phase transmission equation. Usually somewhere between 4 and 5 is what happens in real life. Of course, in real life, the propagation scenario is far more complicated than what I make it appear here, in the sense that you have fading that changes over time, and you have to account for all of these issues. But as far as a system engineer is concerned, most of the times they will basically make this type of an assumption to at least have a reasonable idea of how much power they have to transmit in order to close the link.